So hi everyone. So it's okay to hear me? Perfect. So today I will do a sort of introduction of lattice-based cryptography and see how we can build efficient constructions using a hard problem on lattices. So I will start really from the beginning. So first with cryptography. So I hope most of you knows about cryptography, but let's go back to the sample use case of sending a message to someone, and you don't want anyone to be able to read it, just the sender and the receiver. So for this, you have two possibilities. Either you share a secret key, and it's quite easier. You can use a symmetric encryption, like AES, and it's fast, it's secure, it's nice. Okay. But in the case you don't share this secret key, or if you want to share the secret key before sending message, you need to use public key cryptography. So what is public key cryptography? It's the idea that you can have two keys instead of one. So here you have the example of an encryption scheme. So you want to send a message, and someone generates two keys. PK is the public one, SK is the secret one. And you give to everyone on your website, anywhere, your public key, and then anyone can send you a message. To send you a message, you use the public key, you encrypt the message using it, and you send it, and the receiver, using its secret key, can decrypt. So we know about public key cryptography since a long time, but how to build this? You want it to be secure, and to be secure, you need to consider what an adversary will do. So an adversary will try to learn something about your message, given C, your ciphertext. Okay. And how do we make sure the adversary cannot learn anything? We prove, or we not always prove, but we want to prove that learning something about the message given a ciphertext, it's exactly solving a difficult algorithm problem. So all the difficulty here is to find nice, difficult algorithmic problems to build an encryption scheme or other construction in public key cryptography. Okay. So today we use two well-known problems, factorization for scheme like RSA, or discrete log for scheme like L-Gamal. It works very nicely, it's very efficient. And to solve those problems, it needs an exponential complexity on a classical computer. But, as you all know, if someday soon or not soon we have a quantum computer, so you will need a very large one, a very powerful one, but still it may happen. There is an algorithm called from Shor, so it was in 1997, to solve those problems using a quantum computer. So it's a problem for cryptography, of course, because as everything we use is based on the difficulty of those two problems, if tomorrow we have a quantum computer and we can solve them, it's not good. Okay. So we need to find solutions, alternative and solutions. That's where lattice-based cryptography arrives. So first, the new goals in cryptography, as I just said, it's resisting quantum computers, and the second one is you don't want to just encrypt message. So encryption is nice. Sending message is nice, but it's not the only thing you want to do. We use cryptography in a lot more applications than that. So that's one of the two goals today in cryptography, and the second one is resisting quantum computers. So for this, we need alternatives. And the post-quantum secure one, which are efficient, because it's complicated to build efficient schemes, and with all the functionalities that we want, not only encryption or signatures, but much more than that. So a few years ago, the NIST, which is the institute, so it's American Institute of Standardization, started a competition to develop new standards in post-quantum cryptography. So it started in 2017, and the goal was to find several, not only one, but several schemes to standardize for encryption scheme and what we call key encapsulations and for signature. So there was in 2017 69 submissions. From them, 26 was lattice-based, so on signature and public key encryption, and there was other candidates, so you can have hard problem on lattices, but also on codes, what we call multivariate also, on the hash-based signature or signature based on a hash function, so it's a bit different. And there was 7 from other assumptions, which didn't stay long. Okay. And from this competition, we saw that lattice-based cryptography, lattice-based construction was very serious candidate. So after 5 years of, so when the NIST start a competition like that, people submit the scheme, and then all the schemes are published, and everyone, all the community start to study the scheme. So first we look, is it efficient, is it secure, can we attack them? So during the 5 years there was some attack on the parameters, on the scheme themselves. Some hypothesis was finally not that hard. So after a few years, we look at the scheme which are still here, still secure, and the NIST they choose finalists like 1 or 2 years ago. And last year, they finally say that 4 of these candidates will be standardized, and 3 of them was lattice-based. So the competition is not over. There will be a another round for signatures, and there will be another round also for maybe for encryption. So they want to standardize several schemes, not only 1 or 2, because even if we are quite confident that lattice-based encryption scheme or signature schemes will be secure, we are not sure that there will not be an attack in a few years. So we need construction from several hypotheses, not only lattices. That's why they didn't stop there. Okay. So that's an introduction to say why we are studying lattice-based cryptography. So I think the reason why there was so many finalists based on lattice hard problem is first because we are quite confident they will resist attacks from quantum computers, but as I say, it may happen that there is an attack, we don't know. We have a strong security guarantees, so we will see today that we can build a security proof for the scheme to really show that the scheme is secure if a problem on lattices is hard. So it gives us a strong confidence on the security of the scheme. And compared to the other hypotheses, like post-quantum one, lattices are really the only one where you can build almost everything you want. I mean, you are not just building signature or encryption scheme, you can really much more than that. And that's, I think, one of the reasons why it's so interesting to work on this topic. And hopefully it's efficient, and it will be, I'm not sure it will be as efficient as what we use today, but we hope it will be efficient enough to be used in practice. Okay. So now, to understand how it works, we will have to go back to the beginning, so lattices and hard problem on lattices. Then I will define the learning with error problem, which is one of the main hypotheses on which we base most of the cryptographic scheme. And we will see how we use it to build an encryption scheme. And then we will see the more advanced, like practical scheme, because what I will start to do is explain how it works. But how it works is not really efficient, so then we will see how we can make it efficient. Okay? So a lattice. Do you all know what is a lattice? Or no, not at all? Does someone know what is a lattice? Yes. Okay. Oh, It's okay. So it will be a bit easier if you already saw, yeah, because you can use it also in other topics than cryptography. So this is an example in dimension 2 with a basis. So a lattice is a discrete subgroup of R to the n, and you can always define it with a basis. So my basis is written by the bi, and they are linearly independent vectors, and the lattice is defined by their integer linear combination, so with ai in z. So we'll see examples in dimension 2, but what we are considering in cryptography are much larger lattices of dimension n, much bigger than that. Okay. What is important for cryptography and for all the algorithmic problems on lattices is that you can define the same lattice with several bases. Some of these bases are very good, so the one on the left is a very good one, and some are very bad, so the one on the right is not very, very bad, but is much less nice than the one on the left, okay? So the more it will be orthogonal and the shortest will be the vector, the nicer it will be, because it gives you more information on the lattice. We define the first minimum as the norm of the smallest or the shortest vector non-zero of the lattice. So I will always consider Euclidean norm. And the first minimum depends only on the lattice, not on the basis. It will be just for a lattice you define the first minimum. It does not depend on the basis. And you can define up to n minima, where n is your dimension. And to define the other one, it's not just the second shortest vector, because you could have them in the same direction, for example. So you take a sphere, and you want in this sphere to have n linearly independent short vector. And the radius of this sphere, where you have the n shortest linearly independent vector, will be your nth minima. I also define the fundamental parallelepiped of the lattice, which is so I think the easiest to see very quickly what it is to look at the picture. So it's this area of how to say it? Yeah, the area between the vectors of your basis. So what is interesting? It's the volume of this area. Because it defines the determinant of your lattice, and it's the same, so you can see it, I think, on this picture. For any basis, it will be the same. Even if the basis is different, you will have the same volume. So the volume only depends on your lattice and not on your basis. And what is interesting is that the minima, the first one and all the other one, you have a bond on them, which only depends on the volume, the determinant of your lattice, and the dimension. So here, n is the dimension. So we know that in a lattice, there are short vectors. We know it because we have a bond on the size of those vectors. But all the question is to find them. So that's the first algorithmic problem on lattices is the shortest vector problem. I give you a basis of a lattice. Can you find the shortest non-zero vector of this lattice? So if I show you a picture like that in dimension 2, of course you can find it. It's very easy. Even if I give you a very bad basis, you can find it. But now you have to imagine this problem in higher dimension, like 200, 500, 1000. And if I give you a good basis, like a basis of very short element, it will be very easy to find it. But if I give you a very bad basis, you can imagine, to go back to my basis on the right here, with very long element, it will become very hard. So this problem is a very hard problem on lattice. But it's a hard problem where you have easy instances, like some bases are easy, and hard instances. Some bases are very hard to solve for this problem. And it's such a hard problem that you can even approximate it. So there is another variant, like a first variant of this problem, called the approximate shortest vector problem, where now you have an approximation factor gamma, and you don't want to find the shortest non-zero vector, you just want to find one vector which has a norm less than gamma times the first minimum of your lattice. So it gives you much more possibilities, but still it stays very hard to solve. Even with a large gamma, we will see it stays very hard to solve. So that's a search problem, right? I give you a basis, I give you a lattice, and you want, as the answer, to find a vector. You also have a decisional version of this problem, which is called the gap SVP, so we'll see why just after. So no, I don't ask you to find the vector, I just give you D, and ask you, is there a vector of the lattice which has norm less than D, or no? So I give you a basis, and you have to answer yes or no. Do you think there exists a vector in this lattice which has norm less than D? So when you see it like that, does it look easier or harder than the other one? Easier, yeah, sure. And this is also a very hard problem, and this is also so difficult to solve, then you can also add an approximation factor. So this one is a bit more complicated, because that's where you find the gap. There is an in-between D and gamma D where there is no answer needed. So no, I still give you a basis of a lattice, and you have to say yes if there exists a small vector Z which has norm less than D, and you say no if all the vector has norm more than gamma times D. So that's where comes the approximation factor. So if you look at the two examples, here it's gap SVP, and here it's with the approximation factor gamma. The first one are two lattices, it's a yes and no instances, and you can see that they look quite close. You imagine it can be quite hard to distinguish between those two lattices. The second one is when you have this approximation factor. So now you see that to have a yes and no instance, the lattices are really different from each other. One has to be much more dense than the other one to be able to have a yes and a no instance. So that's the intuition to say, okay, now I had this approximation factor, and it becomes easier to solve, because my two lattices will be quite different if I have a yes and a no instance. So I hope it will be easier to solve. But that's quite the same as SVP, the search variant. Actually, it will be also very hard to solve. So something interesting here, and that we need in cryptography, is that SVP in the search and decisional variants are two problem equivalent. So it's not usual that you have a decisional and the search variant that are equivalent to each other, meaning that if you can solve the search, you can solve the decisional. It's always quite easy, but also if you can solve the decisional problem, you can solve the search one. So it's not true anymore when you had the approximation factor, but still, it's an interesting property of those two problems. And there is another class of problems on lattices. So we saw the shortest vector problem, and there is also the closest vector problem. So it's a bit different. Now I give you a lattice and a target, T. And the problem asks you to find the shortest point of the lattice, which is the closest of T. Okay. so the closest vector problem. You want to find the closest point of the lattice of your target. And as for the previous problems, we can also allow an approximation factor. So instead of just one solution, you have several solutions. You just want an element of the lattice which is close enough from T, like with a norm which is less than gamma times the distance of T on the lattice. So those two problems, so SVP and CVP. So from now I will say SVP and CVP, so I hope it's not too many short. Wait, sorry. Okay. So those two problems are not really equivalent, but if you know how to solve one, you can manage to solve the other one. So they have the same, we will say they have the same complexity. So how hard it is to solve them? It really depends on your approximation factor. So remember, gamma is your approximation factor, so it gets easier when gamma gets bigger, okay? So if you take the original SVP, CVP for gamma equal 1, those problems are shown to be NP hard. And they stay NP hard until gamma, which is, we will say, constant. When you arrive to gamma equal to square root of n, you are in NP which intersect co-NP. And now you are quite sure it's not NP hard anymore, but it's still very, very hard to solve. The best known algorithm, so on the top, the cost to solve it, are still exponential in the dimension. Okay. You can go up to gamma, which is polynomial in the dimension of your lattice, and it will stay very hard to solve. The best known algorithm for gamma, the approximation factor polynomial in the dimension of your lattice, is still an exponential, still have an exponential complexity. And when you take a very, very high approximation factor, like 2 to the n, so exponential 1, then you have a polynomial algorithm to solve them. So it's LLL, which has many algorithms which do a bit better, like BKZ or algorithms like that. But still, you need an exponential approximation factor to be able to solve those problems. But as I said, it's really depending on the basis you give. If you give a good basis, it will be easy to solve. So you know that those problems are, in average, very hard to solve, but it depends really on the instance you give at the beginning. Okay, so the cryptography, what we need is, we need hard problems, very hard problems to solve, and so we use the hardness of those problems with polynomial approximate factor in the dimension of the lattice. So all lattice-based cryptography relies on a conjecture, but like all cryptography, and it's not only lattice-based, but this one is the one for lattice-based crypto. You need a conjecture, and it says that there is no polynomial time algorithm that approximates this lattice problem on their variants, because there are many variants, with polynomial factors. So when we say polynomial, it's in the dimension of the lattice. And that's from where we start, from this assumption, that those problems are very hard for polynomial approximation factor. Okay. For now, it's all good? Perfect.
So why don't we give cryptography on where we can approximation factor? Yeah, for example, why don't we give cryptography for smaller approximation?
We would like to, but we we will see a bit later. But in the proof, we can't, because we will have a security proof which has conditions on the parameter, and the parameter asks for polynomial approximation factor. But of course, we would like to have a smaller approximation factor.
Just for the
That's a good question. What I can say is that for now there is no better quantum algorithm to solve them. But in terms of complexity class, honestly, I'm not sure. I should have a look. Okay. So no, as I said, we cannot use them directly because there are these problems that you have some lattices which are very nice for cryptography because it will be very hard to solve, but some other where it will be very easy. So we don't want easy instances when you use cryptography. So to solve this problem, Regev in 2005 introduced the learning with errors problem, which I think is really at the heart of lattice-based cryptography. So we will define it properly, but to have an idea of what it is, it's really solving a linear system with m equations and n variables. But this linear system is modulo an integer q, so in my example it's 23, and it has noise, so it's not exact equations. Meaning that each approximate means it's not really the first line, for example, it's not really 16, it may be plus or minus 4 or 5, you don't know exactly what it is, but you have a noise, and this noise will make all the difference between solving a linear system or solving the learning with errors problem. So before I define it properly, I need to recall some definition on Gaussian distributions. So I think you all know the continuous Gaussian distributions. So I just recall my definitions. But what I need will be discrete one, meaning that you have the same distribution, but you have a condition that all the x will be here and z will be integers. Okay. It's not really the same that rounding your continuous Gaussian, it's a bit different, but it gives you elements from a Gaussian distribution which are integers. So you can do it on z, on integers, but you can also do it on lattices, that we will see just after. And those Gaussians, they are very interesting properties. They allow to show a lot of things for LWE and other problems, so that's why we need them. And what is the most important property here is that when you use a sample from a Gaussian distribution, you are very confident that those elements will be short, like they will be in the top of your Gaussian. So when you use a sample from Gaussian, you have this very high probability that the norm of your elements will be short compared to the parameter of your Gaussian. And I can do it on Z, but I can do it also on any lattice. So we will not see today how we draw a Gaussian from lattices, but there exist samplers. So this one was one of the first one, but now we have better ones than this one. So given a basis of a lattice, given the dimension, a parameter, the center, you can sample from a distribution which is close enough from a Gaussian distribution on a lattice. So it will give you elements close from their center, but which are in your lattice. So the intuition is that it's quite easy on Z. It will be a bit more complicated on a general lattice, but we know how to do it. And what is very important here is that the parameter you can have, because I said that when you sample from a Gaussian, you can have short elements with short norms, depending on your parameter. But the parameter you can use will really depend on your basis. Meaning, if I have a bad basis with very large vectors, I cannot sample very short elements with my Gaussian sampler. No, I will only be able to sample elements linked with the quality of my basis. So I have this condition of on the parameter, B tilde is a Gram-Schmidt basis. So the parameter cannot be smaller than the quality of your basis. We'll use them again after. You will see where we need it. So to use Gaussian on the lattices, I define the smoothing parameter, so I will not define it really properly. I will just give the intuition. The idea is that you have a parameter which allows to make sure that your Gaussian sampling will be good enough and you will have good property for it. So if your parameter is higher than greater than the smoothing parameter of your lattice, you will have very nice property for your Gaussian sampled on your lattice, which are quite the same as in a continuous one. So in particular, your element will be short, so around their center. So this is the first item. So the probability is that the norm of x minus c, so the center is larger than the square root of n times the parameter, will be very small. So 2 to the minus n for large enough n, it's fine, you're quite sure it will never happen. And the second good property is that you can add 2 Gaussian of the same lattice and it will still give you a Gaussian. And the smoothing parameter is quite easy to evaluate for a lattice. It's linked very closely from the nth minima. So we know for a lattice what is the smoothing parameter. So we will assume for the rest of the talk that it's fine to sample Gaussian from Z, from lattices, and I will do it quite a lot. Okay. So now we can define properly the learning with our problem, so LWE. So I have several parameters. N will be the dimension of the secret. Q the modulo, and alpha will be the parameter of the Gaussian. Okay. And for any S, which I will call the secret, so in ZQ to the N, I define a distribution, which is I sample uniform A in ZQ to the N. And for each of these A, I will do a scalar product between A and S and add this noise, which is sampled from a Gaussian. So I build my linear equations, one by one, A, AS plus E, and I do this several times. So I can say I did it m times, or I can even do it a lot without counting. I can have I can have all the samples that I want. Sorry. And now I have a problem with 2 variants, a search and a decision one. The search variant is, okay, for any S, I give you an arbitrary number of these samples, and you have to find S. So it's really what I saw before, a linear equation, a system of linear equation, but with noise. The noise is a Gaussian. I give you an arbitrary number of those equations, and you have to find the secret. That's the search version. The decisional one is, now I want you to distinguish between sample from this distribution and uniform sample. What does it mean? It means that you have a kind of game with an oracle. So you have a challenger and an oracle, and the oracle will give you either elements from the distribution, either elements uniform. And you have to decide in which case we are. So you can ask as much as you want, and it continues to give you always the same. The oracle cannot change what he is doing in the middle. So he gives you either only LW samples, either only uniform samples. And at some point you have to decide which one is it. So when we say with a non-negligible advantage, it's because you can say, okay, I have 1/2 chance it's one and 1/2 it's the other one, so I just take a uniform bit between 0 and 1 and decide which one is it. So I will have 1/2 chance of finding which one is it. So you don't want this, you want that with that you have more than 1/2 in your probability of winning this game. So that's what we mean by distinguish. Did you see already this notion, or? Yeah? Okay, good. Kind of. Okay, now we defined it, we can have a matrix, like a matrix version of LWE, which I think it's a bit easier to understand. So it's exactly what I just defined, exactly the same. This big matrix A, you can see it as the small a before it's the row of the matrix. Now A times S, it's each row times S, it's the scalar product between the small a and S, plus this error, which is Gaussian. And why is it Gaussian? Because we need it to be small compared to Q, because all of this in this is Q, so modulo Q. So it's really the important. It's really important for what we will do after, to have in mind that when we say small, it's compared to Q. And we still have auto variance. So the third version is I give you A and B equal AS plus E, and you have to find S. And the decision version, I give you A, B, a couple, and you have to decide, is B uniform or is B equal AS plus E? Okay, now if we think a bit about it, we I think easily say that it will really depend on E. Okay. Easy example, what happens if E is equal to 0, if there is no noise? Is it a hard problem? It's very easy to solve, everyone knows how to do it. So we don't want to have a noise which is too small, okay? Too small will not be good, because if we can go back to 0, we will be able to solve it. And now what happens if my noise E is uniform? Uniform in ZQ.
It's going to be hard to recover S for the one.
Yeah, you even lose the information of S. So if E is uniform, AS plus E will also be uniform, and you lose all the information. So it's not interesting, like it's hard problem, so it's nice, it's hard, but it's not interesting because you lose the information and the secret. So the choice of the noise, of the error, is very important here. And we don't choose a Gaussian distribution just like that. We choose it because it's an interesting one where we can prove that it's an hard problem. But first, I told you before that we have something interesting in SVP, is that the search and the decision version are equivalent. And it's the same here. And it will be very useful to build cryptographic construction after. So I will show you quickly why is it equivalent. So you have really these two reductions. One is easy and the other one is a bit more complicated, but still works. That you have, the first one is from decision to search. If you can find S, you can distinguish. So it's not direct, you have one step to do it, but it works very well. So how do I do that? If I find S, how do I distinguish between B uniform and B equal AS plus E? I just compute B minus M times S. So I have an oracle. I give it AB, the answer S, and I compute B minus A times S. And I have two possibilities. Either it is small, in this case I recover my noise, and then it should be an LWE sample. Either it looks uniform, like in this noise I have several coordinates, so either they are all small, in this case I'm sure it's a noise. Either they are between 0 and q without any bond on the size, and then I know it's uniform. So this one is quite direct. But I also have the other direction. And it's very interesting because we don't have that for all hard problems. Like if you know about, for example, the log discrete, the discrete log, sorry, the computational Diffie-Hellman and the decisional Diffie-Hellman, you know that you don't have the equivalence between CDH and DDH. So the other way, if I know how to distinguish between a uniform sample and a LWE sample, I will be able to find the secret. How do I do that? I have an oracle which is able to tell me which case is it. Is it uniform? Is it LWE? So I will use it to find all the coordinates of S. So it's not an efficient reduction at all. It's a very bad one because I will test every possibility for each coordinate. But I don't care, it's polynomial, so it's fine. We have a way to do it much more efficient. We have a much more efficient way to do it, sorry. But this is to understand the idea of why is it possible. So I receive an instance AB, and I want to use the oracle of the decisional variant to decide to find the first coordinate, for example. So I modify it. I modify each sample by adding to AB this new vector, which is U, a uniform element, a lot of 0 for the A, so enough 0 to have A plus U 0. And to B, I had U times S star 1, which is my guess for S1. So I guess S1 should be S star 1. If it's true, I will have an LWE sample. If it's false, B will be uniform. Why? Because this sample, AB plus this vector, I can rewrite it as A prime. So A prime will be A so it's A plus U. So you have A1 plus U, A2. So this is A prime. And then when you do the scalar product between A prime and S, you will find the scalar product between A and S plus U times S1. So you can rewrite it as A prime, the scalar product between A prime and S, plus E plus U, which is uniform, times S star 1 minus S1. So if S star 1 equals S1, if you have the correct guess, this term will be 0. So it will be only A prime S plus E. It's a valid LWE sample. The oracle will be able to tell you it's an LWE sample. Otherwise, it is not valid. If S1 star is different from S1, you will add something uniform to your sample, so your second term will be uniform. So if the second term is uniform, B is uniform, the oracle tells you it's uniform. So by using this a lot of times, so for each coordinate you have to do it q times, because for each coordinate you have q possibilities, you can find all the coordinates of your secret. So it's not efficient, as I said, but it works and it's polynomial and it gives you an equivalence. But we have a better way to prove this, just to give the idea. Okay. So before I continue, I have a second problem to define, which is a short integer solution problem. I define it in the same slide and LWE because it's the same matrix A. In one case, I give you A, S plus E, and you have to find S. In the other one, I give you the same A, but this time I want you to find me a short X in the kernel of A, so a short X such that X times A equals 0 mod Q. So here the condition and the norm of x is very important. Again, if we have no condition, if I just ask you to find x such that x times a equals 0 mod q, it's the same as solving LWE without noise. It's easy. You are all able to do that very quickly. But if I ask to find a short vector, it becomes very hard. So the choice of this bond beta is very important. And the intuition is, why is it hard to solve those two problems? The first one, cis, is exactly finding a short vector in a particular lattice. So this one. All the x in z to the m such that x times a equals 0 mod q. And the second one is like a closest vector problem in another lattice, where you can imagine that the noise you had, so a times s will be a point of your lattice, and the noise you had will go outside the lattice, and you have to go back to find which s it is. So those two problems, they are lattice problems, but when I define SVP or CVP, I said you can give. Yeah.
Why is it a short vector problem in the left problem? Because you can take any x.
No, you want a short one. You want the norm of x to be smaller. So it's a short vector problem.
Sorry.
No worries. So what I was. I said that those two problems, I told you given any lattice, you have to solve them. So when I say given any lattice, it means it really depends on the basis of your lattice. There are good bases, there are bad bases. If I give you a good basis, it will be very easy. If I give you a hard one, it will be very hard, but I'm not sure which one is a hard one. Why do we define cis and LWE? It's because it's also hard problem on lattices, but this time the lattices are defined by a uniform matrix A. So we call them we call them average instances, which means that they will always have the same the same difficulty because of this average instances and the fact that A will be sampled uniformly each time differently. And that's the difference between the two family of problems, and that's why we can use those to build lattice-based, to build cryptographic constructions, and not the first one. But I said, okay, it's solving SVP, CVP, but we want to have to be sure that it's really hard problems. And And so first we can think about how hard it is to solve LWE. The first idea you can have is say, okay, I will try all the possibilities. Okay, I try all the secret, and if b minus a times the secret is small, then I probably found the secret. So there is only one solution. So the cost is around q to the n. Another possibility will be to say, okay, I guess the first n error, hoping they will be small enough or not. It will really depend on the size of the error. Once I guess 0, I can find a secret and see if I was right or not. So the cost will be a bit better, really depending on also the size of your error. The only way to do better is to consider LWE as a lattice problem, so as we just did in the slide before. You have a lattice, and solving LWE will be solving CVP in this lattice. So to solve CVP, you can use, so it's not directly with LLL or BKZ, but you use them, and it will give you this cost. So solving LWE will depend not on only the dimension, but really on n log q. And it's quite intuitive because S is in ZQ to the N. So finally, find S is find N log Q bit. So that's how you can intuitively understand why it depends on n log q. And it depends on the size of your noise. So this is this log square alpha. So the cost will be exponential in your dimension, and really depending on your size of the noise. So that's the best, maybe not the best because some progress since the last years, but the best known algorithm to solve LWE have an exponential complexity. Yeah. It depends. It has to be more than n. So, like n log q, or because after when you build a scheme, you want also to be efficient. So you don't want to have a too large m, because it will increase the size of your lattice, of your matrix. Sorry. So the first thing we know is that the best algorithms are not efficient at all. They have an exponential complexity. This is very nice. But we even know more than this. We know that there are reductions which show that the learning with our problems is at least as hard as approx gap SVP. So at least as hard as a hard problem on lattices. So why is it a worst case to average case reduction? Is because in one case for learning is 0, as I said, you have uniform instances. A is uniform, so we call it an average case problem. And in the other case, it's for any lattice. So if you can solve LWE for an average case, a uniform matrix A, then you can solve gap SVP for any instances. And any instance, it's the easy one, but also the worst one, the very hard one. So that's why it's nice reduction, because it gives you a very strong argument to say that the LWE problem is at least as hard problem on it. So those proofs they were built from Regev in 2005. So the first proof was quantum, meaning that it needed a quantum algorithm to do the reduction. A reduction is an algorithm saying, okay, if I can solve the first problem, then I have an algorithm which solves the second one. And the first reduction was quantum, so you needed quantum algorithm to solve the second problem. Which means that you needed, in theory, a quantum computer to solve the other problem. If one day you manage to solve one, you would have needed a quantum computer to solve the other one. But after, there was a classical proof, but with a loss in the parameter, but still, we are very confident today in the fact that LWE is a very difficult problem to solve and a very strong problem to build lattice-based construction. So this is for the case with a Gaussian error, but it's not the only case, because after a few years of building constructions, we realized that Gaussian is maybe not the best idea to build constructions, because it's not very efficient, for example. It's not that easy to sample. So you can change the distribution. You can, not everything is working, but for those you have proofs that it's still correct if you modify the distribution. And sometimes we use other distributions without proof, but just arguments that it's not easier. So the first result was to say, okay, the error is Gaussian, but the secret can be Gaussian too. Actually, the secret can be uniform in 0, 1 to the n. It can be binary. It's much more efficient. And you have even proofs which shows that the secret doesn't have to have a precise distribution. It's enough to know its entropy. If it has enough entropy, you can show the problem is still hard to solve. So that's for the secret. For the error, the first proof was with Gaussian distributions. So continue, discrete, or discretize, it works. But you can also say, okay, I just need a small problem. So I don't need it to be Gaussian. I can have it uniform in a small interval. It also works. It's a bit more complicated with binary problems because it will not work for any condition. I mean, if you have binary error, you see that for a few samples it will be fine, but if I give you too many samples, binary mean half of them will be with no error. So if you have too many samples, you will be able to solve the problem. So the condition for binary samples is quite small m compared to n. You cannot give an arbitrary number of equation if you have a binary error. So it's a shame because it would have been very efficient in practice, but we don't use this one in practice. Okay. So for now, we discuss the first part of this picture. We start from our problem on lattices, and we show that we have the learning with our problems, which is also a very hard problem, on which we can start building a cryptographic construction. So the second part today will be, okay, I have this problem, how do I build an encryption scheme? So I just recall the definition of an encryption scheme. As I said at the beginning, I want to send a message to someone, and I don't share a secret key. I have two keys, so to have those two keys, the public and the secret one, I need a key generation algorithm that we call keygen. So it takes as input the security parameter. So the security parameter means that the security of the scheme will be in 2 to the lambda. So the best attacks will be in 2 to the lambda. So if you want, if we say we have 80 bits of security, it means that you need 2 to the 80 to attack the scheme. So 80 is not good enough today. The smallest we can take is 128 for the security parameter. So the keygen algorithm generates the key. The encryption scheme takes the public key and the message and outputs the ciphertext. And the decryption algorithm takes the secret key and the ciphertext and outputs the message. What you want is when you decrypt with the secret key an encryption encrypted with the public key associated of the message, you recover the same message. That's what we call the correctness. You want the scheme to be correct. Then when you send a message to someone, this person receives it and he receives a good message. How we do it using LWE. So you will see it's quite easy. I told you that I give you A and B, and the goal was to recover the secret S. So that's exactly how we build the keygen algorithm, how you build your key. Your secret S will be your secret key, and AB will be your public key. So A is uniform, and B equal A times S plus a noise, which is a Gaussian noise here. And that's your public key that you give to everyone. Now to start, we will start to encrypt just one bit, okay? Either I encrypt 0, either I encrypt 1. We start slowly. So M is either 0, either 1. And in a public key encryption, you need some randomness. You cannot have a public key encryption which is deterministic. It doesn't work because anyone can encrypt. So as everyone has a public key, if it always gives you the same ciphertext when you encrypt, it's quite easy to find information on your message. No, a public key encryption needs to be to have some randomness. And so here, R is your randomness. It's a uniform vector of 0 and 1 of size m. So to encrypt, I just multiply A by R and B by R. And to R times B, I add Q over 2 times M. So either if M is 0, I don't add anything. Either if M is 1, I add Q over 2. When I multiply R by M, R by A, sorry. R is only 0 and 1. So it's kind of choosing some row of A to add them. And each time I encrypt, I choose different row to add. So I use the same public key AB to encrypt, but each time with my randomness, I will choose different rows to add, and then I will have something different. So I use the same one for A of B, of course, to be able to decrypt. So UV is the encryption, and now that you have that, to decrypt, you compute V minus U times S. So S is your secret, sorry. You can use it to decrypt. You have to use it to decrypt. So V is R times B plus Q over 2 times M, and B is AS plus E. So if you do the computation, you will see that the R times A times S block will simplify. And at the end, you only have something which is small, so it's R times E plus Q over 2 times M. And when I say small compared to Q. So if it's close from 0, because if the bit was 0, if M was 0, it's only the small part, there is no Q over 2 times M, I return 0. And if it's close from Q over 2, I return 1. So when you compare to other encryption scheme, you have a major difference here, is that the decryption is not deterministic. Meaning that it may fail. But you choose your parameter to be sure that it will not fail. But you have some part of possible error here, depending on how small is your small part, R times E. Is it okay for everyone? Yeah? And what you can show is that if the LWE problem is hard, then this scheme is secure for the in-CPA security. So we'll see just after what it is. So just to give a bit more detail on these small elements over there. The small elements, it's R times E. R is uniformly chosen in 0, 1 to the M, so it has norm bounded by square root of M. E, it's a Gaussian elements. You know the parameter, so you can also have a bound on the norm of E. And then you can make sure, if you choose correctly the parameters, then R times E is small enough, like less than Q over 8. And then if you draw this picture between 0 and Q, if you are around Q over 2, you show that the M bit was 1. And if you are close to 0 or close to Q, you are sure that your bit was 0. That's how you decrypt with a good success probability. So it really depends on the choice of your parameters to be sure that you don't make mistake by decrypting. Okay. Now we want to show that the scheme is secure. That's the nice part, that you can link the security of the scheme to the problem. So the security of an encryption scheme, maybe you already know it, so in this case you're not surprised, but if you never ask yourself what does it mean for an encryption scheme to be secure, the good intuition is that it cannot be I cannot find the secret key or I cannot decrypt. It has to be much more than that. So the idea is that you cannot find any information on the message given an encryption. So given the ciphertext, I cannot find any information on the message. So to do that, to have that, I need the ciphertext to look like uniform. Then I will be sure that if it looks like uniform, if I cannot distinguish it from a uniform distribution, then I can not learn any information from my ciphertext. And to modelize this, we use games between a challenger and an adversary. So the adversary tries to attack the scheme, and we modelize his interactions with the challenger by a game, which kind of looks like what would happen in real life. So with some differences, small differences, but the idea is that. So here in real life, the challenger has his keys, and he gives its public key to everyone. The adversary knows the public key, and he can, so that's a bit more than what he could do in reality, but he can choose the message on which he will run his attack. So he runs his attack on two messages, M0 and M1, that he sends to the challenger. You have two experiments, the experiment 0 and the experiment 1. In the experiment 0, the challenger encrypts M0. In the experiment 1, the challenger encrypts M1. Okay. And at the end, the adversary has to guess in which experiment are we. Did you encrypt M0 or did you encrypt M1? He has to guess, to decide. So he always can say, okay, I have no idea, so I always answer 0, or I flip a coin and I answer 0 or 1 with probability 1/2. And to capture this, we define the advantage of the adversary in this experiment, which is the probability that he answers 1 in experiment 0 minus the probability that he answers 1 in experiment 1. Meaning that the view of the adversary will not depend on the experiment. He doesn't have a better chance to answer 0 or 1 in one or the other case. He will always answer the same thing, even if you change the experiment. That's what you want. You want this advantage to be smaller than a negligible function, to be sure that your adversary have no chance to attack your scheme for the in-CPA security. So in CPA, it means indistinguishability. Sorry. Okay, indistinguishability under chosen plaintext attack. The indistinguishability of the ciphertext under a chosen plaintext attack. Chosen plaintext attack comes from the fact that the adversary chooses the plaintext and that he can encrypt himself the plaintext. Okay? He has the public key, and with the public key, he can encrypt. So he can have as much encryption of M0 on M1 as he wants, but it will not give him information on C. Because we have this randomness, and each time you encrypt a message, it will give you something different. Okay? It's fine for everyone? Now, the goal of the security proof is to show that if you have an adversary which succeeds in attacking your scheme, your encryption scheme, with a non-negligible advantage, then you can use it, you can use the answer of the adversary to solve a difficult problem. Here, we will show that if we have an adversary that can attack the regex encryption scheme with a non-negligible advantage, then you can use it to solve LWE. So I'll just recall how we can see decision LWE also as a game between a challenger and an adversary. That's why I wrote kind of here. You sample A, S, E. I just wrote A, but you also have S and E. And you have two cases. The random case, which corresponds to the experiment 0, where B is uniform, and the LWE case, which corresponds to experiment 1, where B equals AS plus E. So C sends AB to B, and B has to decide in which case he is. Is it a random experiment, or is it an LWE experiment? And we define the advantage of B the same way that we define the advantage of A. And when you have this experiment, before I continue, I just have to explain this. So what makes the regex encryption scheme secure is this leftover hash lemma, which is very important here. As I said, the intuition behind the security of your encryption scheme is that your ciphertext looks uniform. And for your ciphertext to look uniform, so I recall that the ciphertext is R times A, R times B, plus something. You need this, R times A, to be indistinguishable from uniform, but knowing A because A is public. And the same for R times B, okay? And this is not straightforward because it could be that you can invert it and find that it's R times A for some R. You want R to stay secret. And for this to work, you have a condition which is very important on the parameter, which is that M has to be more than 4n log Q. And if you have this condition, you have here matrices which are very rectangular. So this is M, this is N. And it will give you enough entropy to hide R behind R times A. So the leftover hash lemma, I will not prove it at all, I'll just say it here, gives you that. Given A uniform on R in 0, 1 to the M, then R times E, knowing A, this is very important, you know A and you have R times A, it's close enough, so it has a statistical distance less than something negligible from a uniform distribution. What do we mean by the statistical distance? Is that for two distributions, D1 and D2, you evaluate them in all element X, and you take the difference for each point between D1 of X and D2 of X. And if the distributions are close enough, the statistical distance will be very small. You can show that for any algorithm A, you have that the probability that, so it's what we use in the experiments, that A given D1 answer 1 minus the probability that A given D2 answer 1 is less than the statistical distance between the two distributions. So if the statistical distance between your two distributions is small, then your two distributions are statistically indistinguishable. And when we come back to our scheme, it tells you that given AB, because here you have AB, R times AB looks uniform, and that's what we will need in the security proof just after. Okay. So now I just wrote again the INCPA security game, but using the Regès encryption scheme. So it's the same game as before, but now we have the good elements in it. So the secret key is S, the public key is AB. B sends its public key to A. A chooses two messages, so I define the public key encryption with only 0 and 1. Like you can only encrypt 0 and 1. So M0 equals 0 and M1 equals 1, but it's fine. You choose in which experiment you are, B, and you compute the encryptions. And then A answer a bit and win if B equals B prime. So it's a bit different as what I defined before. I define another way I use another way for defining this security. Now I say that if R win with probability less than 1/2 plus something negligible, then what? The adversary will not be able to attack the scheme. So it's just the same game, but written a bit differently. And Now we can have a look at the proof. So the idea of the proof is I have three entities. I have C, B, and A. B and A, they are playing the INCPA security game. And C and B, they are playing the LWE, decisional LWE game to distinguish is it uniform or is it an LWE sample. Okay? So what I want to do is to show that B, if A is able to attack the scheme for the INCPA security, then B can use it to decide whether B is uniform or is an LWE sample. So if A can attack the scheme, then B can use it to solve decisional LWE the game is playing with C. So how it does that? It starts with C sending to B AB with two possibilities, either B is uniform, either B equal AS plus E, okay? And at the end, B has to decide in which case we are. So what does B do? He says, okay, no, I have this public key. I don't know the secret key, but it's fine. I will use it without knowing the secret key and say to A, here is my public key, it's AB. A is choosing M0 and M1, and B will encrypt one of them. To encrypt, he doesn't have to know the secret key, so it's fine. He can do it with AB, even if he does not know S. He sends the ciphertext to A, which computes a bit, and send it to B, and B say, okay, if B equal B prime, I output 1, else I output 0. Now if we analyze this, we have two cases. We will analyze it from a B point of view. The first case is that the small b from AB is uniform. If it's uniform, then my ciphertext R times B is uniform because I lost the information. There is no information in this. It will also be uniform. If it's really uniform, we lose the information of the message. So if we are in the random case, when B sends C1, C2 to A cannot distinguish, A thinks it's a valid ciphertext, but it's not. And as it's not, A cannot distinguish between the two cases. So A has no advantages in this game if we are in the random case. So if we are in the random case, the probability that B outputs 1 is exactly 1/2, because A cannot have any advantage in deciding in which case we are, okay? Because we are in the random case. That's the first case. The second case is the LWE case. No B equal AS plus E. So if B equal AS plus E, we are exactly in the regex encryption scheme case, okay? The game between B and A is exactly the INCPA security game. So A will have exactly the same view of the experiment in this case. Then the probability that B answer 1 in the case of LWE will be exactly the probability that A win. Okay? And if we put everything together, it works nicely. So to conclude, the advantage of B, it's the probability that B answer 1 in the random case, minus the probability that B answer 1 in the LWE case, and it's exactly the probability that A win minus 1/2. So it's a kind of simplified proof, but it's really the idea behind. And then you show a link between the probability of success of A and the probability that B, the advantage of B in distinguishing between the LWE, the decisional LWE, between the LWE sample and the uniform one. So if R succeeds with a non-negligible probability, then there exists an epsilon non-negligibles such that the probability of R win is more than 1/2 plus epsilon. Then the advantage of B is more than this epsilon, and then you can solve LWE. So it shows you that if you can attack the scheme with the INCPA security, then you can solve decisional LWE. what I explained you from the beginning is that LWE is hard problem because you can show is at least as hard problem on lattices. So with those two proofs, you say, okay, no, the security of my scheme will rely on the hardness of those hard lattice problems. So that's why we call that lattice-based cryptography. So now I have my full picture of the beginning I have a link between the lattice hard problems on LWE and a link between LWE and my construction using the security proof. So that's very nice, and in cryptography it gives you a really strong confidence that this encryption scheme is secure and that it's a good idea to use it. So there are a lot of conditions and parameters that I didn't show at all here. So you have to imagine that for the reduction to hold, you have the approximation factor, which is large enough. For this one to hold, you have conditions on the dimension, on the parameters, and everything. So I didn't mention them at all, but keep in mind that it only works because we have a good choice of parameter. And at the end, it's a very secure construction. But it's secure, but is it efficient? What do you think? So if we consider this matrix, n has to be at least 512. M has to be much larger than, so n log q. So it gives you large matrices. You have to multiply them. Thanks. With vectors, so multiplication between large matrices and vectors, it's a quadratic complexity, so it costs a lot. You have to put this in memory, it also costs a lot. So it's very secure, but it's too costly in practice. And tomorrow, we will see how we can do much more efficient than that, but it will be for tomorrow. So maybe, yeah, okay, thanks.
Thank you, Adeline. Any question for our speaker? So maybe just a little one. In Denis' competition, there survived just almost just encryption with lattices. It means that efficiency will come in briefly.
Yeah, tomorrow we'll see that.
Or that quantum computers are not coming and not
are
not coming. So
so we are not worried of the solution, right?
Yeah.
I cannot say if quantum computers are coming or not.
The question is, do we have any evidence for lattice-based cryptography to be non-breakable by quantum computers? I mean, beyond the fact that we don't have any quantum algorithm yet, do we have any hardness results in the quantum world?
We just rely on the fact that researcher tries, which is a beginning, but no. But as I said in the beginning, all cryptography relies on assumption.
Yeah.
Among the candidates which have been kept by NIST, does they rely on this problem or the structural one that you present tomorrow?
It's only the structure one.
Okay.
So we will see them tomorrow. This one, there is one on this one, Frodo, and it's. I think they kept it as for the last round. I think for the fourth round. Yeah, I think so. So there is another round for some of them, which could be useful, but they still don't know. So I think they kept Frodo, which is an LWE, which is quite exactly a regret scheme, actually.
Other questions? Okay, let's thank Adeline again.